additive manufacturing and advanced materials joining and things like that. Last 20 years, I've really been in executive roles focused on technology commercialization. So really, I think it's great to be part of the IAB and looking forward to learning more. Thank you.
Thank you, sir. I appreciate it. VJ, would you like to go next?
Absolutely. Thank you all for having me. Vijay Kamineni, Chief Innovation and Technology Leader for Logan Aluminum, based out of Russellville. I'm from Bowling Green as well. Hi, Chris. And part of WKU Research Foundation for Logan Aluminum. This is important to me. I'm really excited to be here and learn from this. My primary role is an Industry 4.0 initiative for Logan Aluminum. We're a plant with 60 acres under the roof with 1,400 employees. We're Our initiative is focusing on human machine rebalancing, which fits right into your human machine interactions space, uh, machine learning and artificial intelligence, advanced data analytics, robotics and robotic process automations. A lot of work as an industry. We are, for the past couple of years, we've been trying to learn these things and find where we have resources, not knowing what's happening in the state. So having this interaction would really help. We were going out of the state, Austin, California, looking for opportunities that we can learn from or do some experimental projects to see the fit of the technology that is coming into the market for our machines and our processes. So this kind of IAB kind of a collaboration would be very, very useful for the industry. Thank you very much for having me.
Thank you, sir. We appreciate it. All right. Lane, would you be willing to go next?
Sure, yes, thank you so much. I'm Lane Ellen Harris. I am a researcher with Alltech and Alltech Crop Science here in Nicholasville. My background is more in plant molecular biology, and so I certainly drawn to more of the plant and lignin membrane development. But I do have some experience here working at Alltech with some of the large scale manufacturing. So if anybody doesn't know, Alltech is a animal and crop nutrition company with most of the technologies based in yeast and bacterial fermentation. And so, yeah, I'm really excited to be here and I appreciate the opportunity.
Thank you, ma'am. We appreciate it. All right, I have somebody here from TechShot. Is that Andy Kirk by chance?
That is Andy Kirk, and I think I'm the only outsider maybe in this group. I'm actually across the river. I'm over in Greenville, Indiana. But over here at TechShot, we develop payloads for the International Space Station, and I'm program manager on what's known as Fab Lab, which is a multi-material fabrication facility. Kind of the holy grail for NASA right now is to develop a way to manufacture metallic items, and that's to sustain missions to the moon and Gateway into Mars. So we have the contract to develop this system, and we've worked quite extensively with the University of Louisville to develop some of the materials to print, and really excited to learn what we've got going on here with the rest of the group and further advance the technology.
Thank you, Andy. We appreciate it.
Thank you.
All right, Russ. Russ Sells, are you out there?
Yes, I'm here. Sorry.
Oh.
My name is Russ Sales. I am the CEO of, I guess we've got 3 different companies now. One being Bluegrass Tool and Industrial. We're an automation company based out of Lexington, Kentucky. We work with companies all over, really all over the world, building equipment and that type thing. But we have industrial distribution in Indiana, Illinois, Kentucky, Alabama, South Carolina, and we really kind of go to market with finding problems that customers have and making solutions, and really the tough ones that most people don't do is really where we get into that. I've worked with universities in the past on their engineering, industrial technology type systems, and that's kind of how I fit into the scenario, and really looking forward to what this is going to bring. So, thank you.
Thank you, sir. All right, I have a 203 number that's called in that I am not recognizing.
This is Madhav Patel with the MHS, Material Handling System, based in Louisville. So, hi everyone. I'm the Research and Development Principal Engineer, Robotics. So I work for MHS, Material Handling System. If anyone knows, we are the #1 courier system integrator in North America in parcel and courier industry, as well as in the distribution center. We are growing faster. We have our biggest clients are like UPS, FedEx, Amazon, DHL, all the bigger courier industries, like along with the USPS. So I have a PhD in robotics. So my research was in the heterogeneous swarm robotics. And then I have almost 10 years of experience, more than 10 years of experience in the robotics and automation, 10 to 12 different international and US patents, 25 to 30 publications and kind of stuff. Our main goal is here in the MHS is develop the automation and the robotic solution for all these bigger companies, where replacing the human being along with their help using the vision, robots, and machine AI systems. So we do use machine learning, neural network, reinforcement learning, all kind of those algorithms to recognize the different patterns and packages, and we use robots to singulate those into the sorter, and that's how they get delivered into mailboxes for shippings and handlings. I'm really excited to be part of this team, and I'm looking forward to it. Thank you.
Thank you, Madhav. We really appreciate you being here. All right. Do I have any other industry advisory board members that have logged in and I'm just maybe not recognizing you based on the login? Have somebody logged in as Alice?
Yes, this is Alice DeSanto from Ragent Corporation. How are you?
I am well. How are you doing this morning, Alice?
I should have put my last name in there. It shouldn't be a guessing game. Sorry, I'm in my car, so I'm not joining you guys by video. So Ragent, if anybody is not familiar, we're based out of Philadelphia Metro, but we moved into the Moorhead area about 6 years ago, and we've got ever-growing manufacturing representation in the eastern part of the state. Upon arrival, we forged a really strong and fabulous relationship with the Moorhead Space Science Program, and the students that come out of there make up 95+% of our employee base in Moorhead, and we're currently employing around 25, and that will rapidly increase with the amount of manufacturing and production that we're doing to closer to 100 over the next couple of years. So our technology is industrial wireless networking, where no infrastructure is required. So really plays strongly in the space for mobility and autonomy for all things. So, from larger autonomous vehicles, because we got our start in the military and then moved our technology into the commercial space for mining. And as we've grown up as a company, this is our 20th year in business, we have now evolved our breadcrumb technology, that's what we call our radio nodes, into smaller, lighter, more agile, less expensive, which is extremely well suited for robotics, ground-based, air, sea. For me personally, I'm the vice president of global marketing for Ragent, and I am based in Louisville, Kentucky. So by de facto, you get me boots on the ground more often than not. And I came to Ragent as a customer. So I was in the robotics space for Sharp Electronics on Sharp's first initiative to introducing robotics into the United States for safety and security applications. So really happy to be a part of it. And just one other thing, we do quite a bit of work with DARPA to continue to push the envelope as far as robotics is concerned. Our latest work with them, I think we were on 3 of the teams that competed in Louisville, a few months back, and then 2 of them continued on to the finals. And our latest project is swarming, where we're actually successfully doing over 200 drones and bots at one time. So pretty cool work.
That's awesome. Thank you for sharing that, and thank you for taking the time to be here with us, Alice. We really appreciate it.
Yeah, sure thing.
All right. And I think that we also have Glenn Elin on the line. Glenn is part of our statewide EPSCoR committee. Maybe Glenn, if you could introduce yourself for those who might not know you.
Yeah, happy to. Thank you for letting me eavesdrop this morning, you all's meeting. Glenn Eaglin, I'm a senior engineering manager at Funai Electric. We're in Lexington, Kentucky. So Funai, an Osaka, Japan-based company, is the company that purchased the inkjet division from Lexmark when they spun that out in 2013. So we're a group of about 50 engineers in Lexington. So my interest in this group is we do advanced manufacturing in Lexington. We have clean room space. We do MEMS work at the wafer level. Since no one really cares about printing anymore, we consider ourselves a microfluidics company, not a printing company. We're doing other applications with our technology, one of them being printed electronics, and we're working with several companies outside the state of Kentucky on that technology. We would love to find interest within the state to continue that work. And then also we're looking at other life science applications for the technology. So that's our summary. Thank you so much.
Thank you, Glenn. We appreciate you being here. All right. I think I've captured all of our visitors, but if I missed anyone, could you please let me know? I want to running a couple screens here. I don't want to overlook anyone. Okay. All right. I think we've gone through visitor introductions then, and I would like to turn the floor over to John Anthony to kick us off. Is that right? Nope. My bad. My bad. I'm turning the floor over to Seth. Seth, can you kick us off?
Yeah. Find this. Let me see. Do you see my PowerPoint?
Yes, sir, we do. If you want to go to full screen, that would be great.
Working on it.
Alrighty, and our program is divided into 4 research thrusts, and so we're roughly going to go in order of how we've listed our research thrust. And so I believe that Seth is representing research thrust 1.
Yeah, thanks so much. It's really really great to present to you all today, and really thinking about you being at the forefront of innovation and taking ideas and concepts and converting them into businesses. Really, our goal is to serve you all. My part of this project is fairly modest relative to the other 2 presenters, as a sort of a glue piece in between the themes that you're going to hear about a little later on. And that's really, when we were developing this proposal, one of the things that we really identified early on was the lack of biodegradability of products that are moving into the commercial space is perhaps an area that's quite fringe. It's kind of outside the box, and we might be able to develop some unique strategies using students and using innovation to think about what could be possible using biological raw materials. And really, I heard someone else speaking about waste streams and thinking about using raw material waste streams that are not commercially viable. They're often diverted off the main resource path, and thinking about how we could use those to create an extra level of competitiveness in the future. I think a lot of folks are thinking about sustainability and thinking about these things right now, but they're really difficult. There's a lot of the times, and I'll give you some examples, is biology just really isn't as good at raw material production and functionalizing things as we would like. So we're going to continue to run into that, but continue battling against the entropy and trying to find solutions. So in our strategic milestones, one of them really was to create biodegradable structural polymers. And if not create them, find them and find that application. A lot of that's not working in the lab and finding something, then finding a place for it. It's listening, and it's listening to our other stakeholders and saying, okay, well, this is your biggest problem and your pain point. How can we work into that with what is existing in nature? And how can we find extraction methods and raw materials that could meet those needs? And so those might be fibers or resins that implement functionally into the structural units that you're going to be hearing about from Dr. Anthony and Dr. Popa. We would love to find semiconducting materials. We would love to find thermally conducting materials and things with structural properties. But in general, just biodegradability is a huge challenge in and to itself. So at this point, we're really working through this phase here, and you can hopefully see my pointer here, where we're really trying to focus in on raw material opportunities. And we are doing this with our friends at the Somerset Community College as well. We're thinking about their ability to 3D print things, and we're engaging in dialogue. It's meant to go out there this week, and with Heather's on, I'm sorry I couldn't make it out there, but hopefully going to go out next week and continue to expand that discussion. And the idea is to really deliver biodegradable structural polymers into printable objects in that sense, but as well as pushing them over towards John Anthony, Matt Weisenberg, Chad Risco, that group, and push them over into their pipeline as well, with the ideas of finding materials that can be used. And really, we don't have to completely solve a problem. A lot of the time, the incremental improvements come in actual commerce, but we are in the point of finding what is possible. And at this point, screening the nature of biology is always a necessary process. Yes, I'll just give you a quick update. We definitely hit delays in COVID that were quite inevitable, but we're really moving back on track right now. This is just a little bit about our pipeline where we hope to be sort of starting into the new year. And we've got biochemistry or chemistry, understanding the biology, pushing the availability, and thinking about where we could get products and what their properties are. Need to understand the toxicity and how they might interface with the environment. Things from nature can be just as harmful as things mined or found in more pure streams. And then linkage to scale. We need to make sure these are commercially viable. And so this is kind of this pipeline that we think about. And then we push these compounds over to our other pillars and our other teams, all located around the state. We've hired a really wonderful young investigator in Kendall Corbin, originally from Kentucky, and she has returned to Kentucky with the Kampers project. So that's really, really great. I'll give you a quick update on her in just a moment. And this is just our bit more of a Gantt chart. But I know I've only got 10 minutes, and this is going to bore you, so I'm not really going to push through this too much. This is Dr. Corbin. She's off and running now in the College of Agriculture, Food and Environment, and often kickstarting projects. We're pushing a project right now on looking at a waste stream from grape must, and that is the leftover material from harvested grapes that are used for making wine. And that is a fairly large waste stream in agriculture, but has a lot of kind of high value, interesting materials that are aromatic and planar and meet some of the criteria that our other collaborators are looking for. And those are anthocyanins, tannins, and flavonoids. And we're looking at unique ways to extract those and push them over to our team. So this is the listening process where we really worked with that the other pillars to sort of think about what products are really needed and where could they be sourced in nature. And we found indigo, anthocyanin, aerone, and flavonols are really meet these criteria. And what's really depressing, and this is part of research, and I know the folks on the industrial side hit challenges all the time, but we were really proud that we were able to get indigo out of these plants and then do some semi-purifications, and we were able to get it up to 70% purity out of plants. And remember, in plants, in these organisms, you got proteins, you just got ash, you got a ton of other structural biopolymers in there, thousands of molecules, honestly, that you're wrestling against. So to get something sort of pure is quite a challenge. And then we sent it over to John Anthony, and he crushed our spirit by explaining that they're doing an experiment where 99.9% purity versus 99.8% purity in indigo created an order of magnitude reduction in conductivity and effectiveness. And so we realized we've got to do something more there. And I'll explain a little bit about what we're working on. But it also really made us consider our functionalization of these is not necessarily in perhaps the semiconducting or really being competitive in that space, but really showing proof of concept and thinking about functionalizing things on a cruder scale, perhaps, with the biodegradability and overall maybe showing programmable lifetime of things, because a lot of these molecules change colors or actually have certain properties that we could use to show lifetime or predict lifetime or breakdown of the material. There's some great team up in Louisville with the Running and Schultz lab, really looking on that second goal there of creating these enzymes that really drive reactions. And they're looking at molecules, nanostructures of electrical and optical properties, and they are really focusing in on a series of proteins, which are really excellent for purity and for improvement there of certain processes. So it's they're using unique sources of plant material. They use a lot of cell culture, tobacco, carrot, geranium, and mosses as their chassis, their vehicles for production of things. So when you're producing things in nature, you often use plants or microorganisms as those production vessels, as I know Alltech are real experts in doing, and you use those to enrich certain material. And honestly, we're kind of meeting our goals right now of hitting our target molecules, and now we're really into this concept of, can we get more of it? Can we put it through this pipeline? And can we drive it over to our other teams? And so we've onboarded Kendall. We're looking at comparisons of quality yield, obviously failing in some areas and having some success in others. Purity is a major driver, obviously, is pretty incompatible with biology, and we're trying to challenge that with some other techniques. And then we're really trying to emphasize raw material waste streams as building blocks for biodegradability. And spent grains from fermentation is a really valuable source and a really massive problem for the bourbon industry in Kentucky. I think there's close to 1 billion tons of spent grains produced a year. Mind you, that's 90% water, but that creates this huge feedstock waste stream that is currently has a very large economic footprint. And we're working with folks, for instance, over at Somerset, the community college there, incredible team there working on 3D printing to try to put some into their hands and also put some of these other functional biopolymers into our team members' hands. as we also look to start cloning the genes responsible for those and creating a gene bank that will be usable for future towards the end of the project. So I'll leave it there. I really thank you for attention. And we're kind of the weirdos in this group with the bio weenies who are kind of separate from the folks who are more the bigger pieces of the pie. So I'll check out here, but really want to mention that nature's building blocks are there and they continue to be untapped, and that we should realize that this is a huge opportunity for us in Kentucky, as well as when we think about biodegradability and the future of sustainability with these products. I think it's going to come to us, so we've got to get going on this. I can leave it there, Rodney. Do you want to ask questions now or move right along? It's up to you.
I think let's move along, and we'll get back to questions at the end.
Okay, thanks for your attention, everyone.
Thank you, Seth. We appreciate it. John Anthony, I believe you are up next.
So at UK, we've got more than almost 20 years now experience in printed electronics. We've collaborated with companies like Samsung, Sony, 3M on printing active backplanes for flexible displays. And we've got growing expertise in printed electronics. And so the whole thought for this operation was, can we hybridize these two approaches to essentially embed electronic functions within the structure of a 3D printed device? Next slide, please. So the functions we're curious about embedding, number one, absolutely is sensing, but you've got to have power, so we need to generate and store the power. You've got to process the data, so we need to be able to print logic. And then communication, we need to send that outdoor, outside the structure. So what we're working on and what I'll talk to you about today is, and not in a particular order, new low power methods for sensing, flexible lightweight photovoltaics for power generation, self-powering redox flow batteries for power storage, printable semiconductors. These are going to be the active components of all the sensors as well as the logic. We've got to have conductive interconnects, so we've got to be able to print those. And also, compliant form factors for, we can either have the material embedded or conform to the surface of an object. Next slide. So let me jump right in. We've got a new faculty member, Aaron Huckabee, who's an expertise is in printed metals in particular. So we're working on printing on a variety of different surfaces, whether they're planar or 3D printed structures. He's looking at new flash sintering approaches to keep the heat low, because the usual sintering approaches to give high conductivity would tend to melt plastics. And so his new flash sintering is working extremely well. And the printed conductors, silver and platinum, are very, very stable. Next slide, please. Very exciting development and enabled entirely by Kentucky NSF EPSCoR was the acquisition of a dedicated spin line for taking PDOT, which is a conducting polymer, and spinning it into fibers. And these fibers enhance the conductivity of the conductive polymer substantially. And this is actually a unique infrastructure, pretty much the only one in this world to be able to spin these sorts of polymers into these long continuous fibers. Next slide. So for 3D printing, what we really want to be able to do is take these conductive fibers and then encapsulate them within the filaments used for fused 3D printing. And so Matt's developed a very nice method on the bottom right. You can see the microgram there of having a highly conductive printable PDOT core surrounded by an insulating polymer matrix. And we're working right now with our next hire, which will be coming up next, to find ways to make efficient contacts between these essentially conductive wires and the semiconducting devices. Next slide. And so Professor Patterson, who was our first EPSCoR hire, we're hoping to get one more, has expertise in organic and printed transistors. So one of the key things she's doing in the upper left is blending the organic semiconductor with printable polymers, either regular 3D printing or inkjet printing, to yield high efficiency transistors, both for gas and pressure sensing. And then she's also on the right working on organic electrochemical transistors. This is a slightly different sort of device, and it's being heavily used in the area of biosensing, sensing things like glucose, for example. And if we go to the next slide, So she's working with the fibers team to actually try to construct these OECT devices on the fibers for electronic textiles. And so again, the idea is this will be able to monitor sweat for an array of electrolytes, glucose, what have you, and then be able to provide feedback directly to the wearer of essentially health conditions. Next slide. So for photovoltaics, we need to have, I love Microsoft. You transform between computers and things go crazy. Oh well. So we need to have a transparent conductor. Light's got to be able to get into the active photovoltaic material. And so they've been working with silver nanowires, doing a variety of different approaches. Two unsuccessful. The most successful is on the upper right, using a C60 fullerene blended with silver nanowires. It retains impressive transmissivity. So 80% of the light makes it through, which is critical if you're trying to harvest light with a photovoltaic. The problem they're having now is that the surface roughness is interrupting the formation of the active material, the active photovoltaic on it. So they're working now, both Aaron and Ken Graham are working together to try and really print or spray print much smoother films for these applications. Next slide. And so perovskites have been the photovoltaic active layer of choice. They're really, really promising. Efficiencies greater than 20%. The problem is traditional perovskites are made with lead, and nobody wants to be wearing things covered with lead around on their clothing. So the team is working on making tin, much more environmentally friendly tin versions. They're having really issues with stability. And so we actually pull in the computational chemists to start calculating how various additives and surface treatments will impact the stability of perovskite-based photovoltaics. Next slide. So power storage, we've gone with redox flow because we can essentially print reservoirs for the flow materials within large structures. And what Christy Trinkle is working on doing is showing how instead of using electrically powered pumps to circulate these liquids together to regenerate the power, you can actually use body movement. So she come up with some very, very interesting microfluidic approaches so that essentially sort of a rocking back and forth is sufficient to recombine these stored negalites and posilites and regenerate the electricity that was harvested. Next slide. So on sensing, biosensing, so the Barron Group is working on using electrochemical changes in living cells to monitor more complex, thank you, Joanna, biological analytes. And so they're actually depositing these cells by 3D printing. And so they have really clever chemistry to coat the cells, keep them safe during a 3D printing process. And they're actually now measuring, in the lower right, detecting calcium ions using these essentially bio-inspired transistor-like devices. Next slide. So UK, U of L, and Eastern Kentucky University are working together on environmental sensors. So they're trying to make ultra low cost so we can distribute them widely, printed electrochemical sensors. They have some really difficult times at the beginning with getting a proper adhesion of the printed gold electrodes to surfaces. But on the lower right, they're using now soluble gold nanoparticles and printing these and actually getting some good electrical chemical performance from these printed gold electrodes, sensing environmental toxins, in particular heavy metals. So looking at heavy early warning in essentially either waste streams or ponds of the pollution of heavy metals. Next slide. We also work a lot with Savannah River National Lab, and they do nuclear power plant decommissioning. And they were very interested in having essentially flexible radiation sensors they could stick onto robotic arms for monitoring radiation in detail. And we kind of spun that off with the Wake Forest Medical Center on making conformal radiation sensors for cancer chemotherapy. Because currently they use these rigid silicon detectors, which silicon doesn't match human flesh at all as far as X-ray detection. So with the organic-based materials, we actually very closely match human tissue, and it's also quite conformal, so it conforms to the shape of whatever surface it's put on. The X-rays pass right through this screen, so we can extremely accurate measure of the dosage in radiation chemotherapy. It's far superior to silicon. Next slide. So finally, along with rigid, we want to look at flexible robotic components. And the idea is if we're printing within or adhering on these flexible systems, we really need to understand how they behave and how things adhere to these surfaces. So on the next slide, Jonathan Pham is looking at various ways of adhering these printed devices onto these flexible robotic systems so that we get good let's say, transmission, for example, of pressure between the sensor and the robotic system. And that wraps mine up. I try to get us back on time.
So today I'm going to talk about a different topic. Actually, John Anthony's presentation was going to discuss how we can take materials that SET will produce and incorporate them in structural electronic objects. So structural electronic objects are composed of 3D prints, embedded sensors, embedded electronics that can be built up sort of layer by layer by 3D printing. What I will talk about today is taking those sensors and materials and incorporating them into robotics, and then using them as a vehicle to enhance the interface or interaction between human and machine, human and robot in our case. So the overall vision of this is on the left side. We have a picture of what a new American manufacturing worker would look like, somebody wearing smart sensors embedded in fabrics or other objects, through which it can sort of disseminate or send intent to control manufacturing processes, for example, robots, but it could be other types of additive manufacturing on the factory floor. At the same time, the machines executing manufacturing commands will also send back a rich set of machine sensor data. And the research here is focused on how to handle massive numbers of sensors on both sides, and how to adapt these interfaces. We call these things adaptive interfaces based on performance metrics, so that the interaction occurs in a more seamless manner or more intuitive manner. The research thrust 3 and 4 complement the first two, where we create sensors and materials. And we would like to essentially integrate sensors to detect human activity using optical fibers and conductive threads embedded in electronic textiles. That's one of the goals of RT3, as well as modeling, understanding, and designing human-in-the-loop robotic systems. So robotic systems that can efficiently integrate the human in the feedback loop that I just described. We are also going to take this technology and raise it to the level needed to actually help advanced manufacturing as well as healthcare. In research thrust 4, the goal is to test these systems and controls software in real-world applications. We have applications including part manipulation and assembly on the factory floor, manufacturing of micro electromechanical systems and devices, as well as larger factory-like activities like in machine shops or condition-based maintenance in manufacturing environments. So the three goals under RT4 are essentially optimizing the human-robot system for part manipulation, assembly, and attachment, developing intelligent manufacturing of micro electromechanical systems, and the next generation machine shop industrial controls, predictive maintenance, and sustainable advanced manufacturing. I want to share a few videos on exactly what this collaborative human-machine interface should look like. And if I play these videos, let me mute them actually, and I don't know if you can actually see them. On the left, you see an example of physical interaction with a robot. Physical interaction means you're going to teach the robot by demonstration, by physically pushing and pulling, guiding it through the motions that are desired. In the center, you see operation of a robotic prosthetic hand using your healthy limb and a sensor glove that's been added to that, and that makes the operation of that prosthetic very intuitive. On the right side, you see an example of how we can deploy these collaborative robots, and again, teach them by demonstration to perform a set of complex actions. And in that case, in that video, the robot is pouring a glass of wine for the user. And also we can use our mind to enhance the collaboration with the robot, where our muscular facial muscle expressions could be used to control the direction of motion of that robot. And also EEG, for example, waves could be used to send the human intent to the robot. And in the center here, you see that this interaction is not unidirectional. It happens both ways, in the sense that if the effect of the interface is not what is desired by the user, then this learning process at the interface will be able to tune the parameters of the interface. So in order to integrate and evaluate different types of sensors into interfaces, we are taking, for example, EEG, EMG, other types of physiopsychological sensors, things that could be deployed on clothing, and evaluate them in applications to control robots, and focusing on, in particular, in intent estimation of the human, adding the human in the control loop, concept of variable autonomy, which supersedes shared autonomy. For example, variable autonomy would be a strategy to let the human do directly complete some of the tasks, and then let the robot complete other tasks depending on the performance, their respective performance in that task. Also providing fault detection or explanations of faults during interaction using machine learning. One of the anchors or the type of sensor that connects our four thrusts is this pressure sensitive robotic skin that could be created by eventually by biodegradable polymers and substrates, and essentially have 3D printed sensors and electronics sort of encapsulated in this structural electronic object. So for example, on the right side, you see a device called the OctoCan. It has 8 sides, each containing pressure sensors. These are pressure sensor arrays. So you'll be able to touch this object, interact with it physically, squeeze it, and get forces applied by your hand onto this object. So this enables various applications, such as placing these sensors on the tips of a robotic gripper, placing sensors on the whole arm of a robot, so we call this whole body pressure sensitive skin, or producing structural electronic devices like the OctoCan that can be then used to create guidance force inputs to the robot. In our project, we are engaging with a large number of faculty from not just U of L, but also UK, WKU, EKU, and Moorhead State. They're all working together with the 5 goals that I listed and a myriad of other objectives. And I cannot actually go through an exhaustive set, so I just picked a few examples to share with you. So there are several objectives. They're all, if you go back to my collaborative HMI diagram, some of them are geared at detecting intent. Some of them are related to which performance metrics that we can use in real time, how to incorporate the human in the control loop. we are also engaging in actual experiments with human subjects here in our lab under IRB approval, and so on. We are using a variety of robotic platforms. Some of them are mobile robots, some of them are industrial manipulators. I just want to go through a few examples. How much time do I have, Johanna?
Oh, really? We're probably getting a little close. 2 minutes. Wrap it up.
So we are developing sensors. I mentioned pressure sensitive sensors. Cindy Harnett here at U of L is working on optical waveguides arrays, which can be essentially weaved into fabric. They work on the principle of time of flight. Essentially, that can be used to detect strains in the fabric. And so if you embed these into a flexible structure and then press on it, you'll be able to detect deformations using optical multiplexing electronic chips. We call these time-of-flight histogram chip that will be able to reconstruct the strains or the deformation in a flexible object. We are using these sensors on a rocking chair. It's called, we call it instrumented rocking chair. In this case, the application is to improve and monitor trunk control in children suffering from spinal cord injury. So this is a medical application, but it relies on detecting pressure patterns during the rocking motion. One of the robots that we are using to conduct research on detecting human intent is this robot shown here called the Adaptive Robot Nursing Assistant. It's essentially a mobile base that you can tug around, or you can actually also drive directly. It has a manipulator arm, and we've implemented this scheme called a neuroadaptive controller, which essentially adapts the pushing cues of the human, takes into account varying payloads or different types of floor conditions, so you can drive on inclines with the same performance as you would on a flat surface. Other things that we're doing is using machine learning to detect human intent through visual sensors. For example, in this application, we can monitor human hands as we conduct different types of operations. This is particularly important on the assembly line where you have a human and a robot working together for the robot to detect where the human hands are. We're using machine learning to develop two types of human-in-the-loop collaborative interfaces. One of them is based on motion imitation, and the other one takes into account and fuses information from a variety of sensors. Like you see here, it could be a worn sensor, it could be conventional sensors like you would have in a joystick, and then fuses those to turn those into navigation commands for a mobile robot in a way that is intuitive. So if you can think about using a joystick to drive a robot, that's very straightforward. But if you have an array of sensor worn on your head, the intuition actually goes away. So the problem here is we want to take those sensors and guide the robot in an intuitive way using machine learning to learn how to do that. I mentioned variable autonomy. In this case, in this example, we were conducting autonomous disinfection using our Arna robot, and this was during COVID. So the idea here is that the human operator can locate objects, can approach objects with the robot, and then can engage something like a spray to disinfect. If the human actually does this using teleoperation, it will take a really long time. So So some of the tasks, while they may be challenging for the robot, some of them could be very quick to be executed by the robot. And so this algorithm will assign the tasks depending on the level of performance of either robot or human to accomplish the best result. And if you see here, targeting is very easy for a robot to do, but other types of fine alignments may be more difficult or easier to do by the manual using teleoperation by the human.
Thank you, sir. You did that great. All right. Thank you to all of our speakers. We really appreciate you taking the time to share the research with the team. And Rodney, I'd like to turn it over to you to maybe talk for a minute about next steps.
Sure. I'll try to keep this quick since we don't want to encroach on your time. We, obviously appreciate any input you would like to provide. You can, send it to any of us and we can pass it along. The other thing I did want to mention, well, two things. One, a goal of this is to be able to make partnerships with industry and do some of the things to get them out there. We have a new program that we put in place within our track one that is for funding emerging ideas and to be able to do that quickly. And the reason I'm saying that is if you see a chance, to partner on some of these things, or if maybe there's someone else in your network that you think that may be a good match, we can actually help seed fund to get that beyond the initial, would this work for what we're interested in? So certainly, reach out for that. We are wanting to be able to fund those sorts of things. So it's a good opportunity to maybe kick things off. We also have a internship program where we will help support one of our students to do an internship with Kentucky companies. Those calls go out on our website regularly. And Zara, can you get Rosemary to send that to everybody? And then the last thing I did want to say is kind of what's the next step with this in terms of these meetings. We would like to get this onto a schedule of maybe twice a year. One of those will be inviting you to what we call our Super Collider event. I know some of you have been to that in the past, and it's really where you get both an update like this, but also our students present on their research and their individual projects. And it's a really good chance to get a better idea about what's going on there. And then we would just include a meeting of you all as part of that. The other meeting we'd like to have with you is probably going to be, that's usually in like February or March. The other meeting we'd like to start looking at having regularly scheduled would probably be around the August timeframe. Obviously, we'll work with you for specific scheduling. Our annual report goes to NSF has to be there before the end of July. They then review it and get back to us. In that includes what our action items are going to be. And so that would be a really good time to go through those with you and get your feedback on those items. And, do you see where we might want to make adjustments or things like that? So that's really sort of what we would like to do as the next steps. You'll be getting an invite to the Super Collider. That is scheduled for February, and that will be when we will host our next meeting. So I just want to say thank you all for taking the time. Sorry about the technical difficulties, and also thank you, Johanna, for getting this all organized.
Absolutely.
Thank you all.
Thank you. Please reach out if there's anything that struck your fancy that you'd like to talk about some more. We'd love to make those connections.
I was wondering if you could send out PDFs of the charts. Would that be possible?
Certainly mine is available. I think, okay. Johanna, follow up with all the presenters and just see if they need to cut anything out before we send them out.
Make any edits. Yeah. Okay.
That's fine.
We'll work on that for you, Chris.
Thank you so much. We're very, very exciting work going on.
Awesome.
All right. Thank you all.
Thank you all. It was a wonderful
Thank you.
presentation. Looking forward to February. Take care.
Awesome. Thank you, VJ. Bye, everybody.
All right, thanks,
Bye.
John.